Transformers are generally reliable components, but failures can happen. The failure rate of transformers depends on several factors including type of transformer, for example dry type or oil-filled, operating conditions such as load, voltage, temperature, maintenance practices, and environmental factors. According to industry estimates, the average failure rate of industrial distribution transformers used in CNC machines and similar applications is around 1 to 2% per year. This means that for every 100 transformers, 1 or 2 may fail within a year. While transformers are typically reliable, some possible reasons for failure include overloading or exceeding the rated load capacity, voltage spikes or surges, insulation breakdown due to moisture, heat, or chemical contamination, short circuits, or mechanical damage. Since most internal causes of the undervoltage alarm have been ruled out, it is possible that the transformer could be contributing to the issue. Here are some steps to take. Firstly, inspect the transformer. Look for any visible damage or signs of overheating. Secondly, check the transformer input and output voltages. Use a voltmeter to measure the voltage at the transformer input and output terminals. If the output voltage is significantly lower than the input voltage, it could indicate a transformer problem. Thirdly, check the transformer load. Determine if the load on the transformer is within its rated capacity. Fourthly, consider the age of the transformer. If the transformer is older, it may be more likely to fail. Fifthly, consult with an electrician if unsure about the transformer's condition or how to troubleshoot further. Consider consulting with a qualified electrician. While transformer failures are not common, they can occur. It is important to thoroughly investigate all potential causes when troubleshooting an undervoltage alarm. Transformers play a critical role in electrical power distribution, stepping voltage levels up or down to meet the needs of various equipment and applications. Their reliable operation is essential for maintaining consistent power supply and preventing disruptions. The specific type of transformer used, whether dry type or oil-filled, significantly impacts its failure rate and maintenance requirements. Dry type transformers, which use air as a coolant, are typically found in indoor applications and require less maintenance compared to oil-filled transformers. Oil-filled transformers, which use oil as a coolant and insulator, are more common in outdoor applications and high-power installations. Operating conditions such as the load, voltage, and temperature exert a considerable influence on transformer lifespan. Overloading a transformer, that is, exceeding its rated load capacity, can lead to overheating and insulation breakdown, increasing the risk of failure. Voltage spikes or surges caused by lightning strikes or switching events can also damage transformer insulation and windings. Maintaining proper voltage levels and minimizing voltage fluctuations are essential for ensuring reliable transformer operation. Temperature plays a critical role in transformer performance. High operating temperatures can accelerate insulation degradation and reduce transformer lifespan. Adequate ventilation and cooling are necessary to prevent overheating, especially in high-load applications. Maintenance practices are crucial for extending transformer lifespan and preventing failures. Regular inspections, testing, and cleaning can help identify potential problems before they escalate into major issues. Inspecting the transformer for any visible damage, such as cracks, leaks, or corrosion, is an essential part of routine maintenance. Testing the insulation resistance and turns ratio can reveal insulation problems and winding faults. Cleaning the transformer bushings and terminals can prevent flashovers and improve insulation performance. Environmental factors such as moisture, heat, and chemical contamination can degrade transformer insulation and accelerate failure. Protecting transformers from these environmental hazards is essential for ensuring reliable operation. Moisture can penetrate transformer insulation and reduce its dielectric strength, increasing the risk of insulation breakdown. Heat can accelerate insulation degradation and reduce transformer lifespan. Chemical contamination, such as corrosive gases or liquids, can damage transformer windings and insulation. When troubleshooting an undervoltage alarm in a CNC machine or similar equipment, it is important to systematically investigate all potential causes. The first step is to rule out any internal issues within the machine itself. Check the power supply connections, wiring harnesses, and electronic components for any signs of damage or malfunction. If the internal components appear to be in good working order, the next step is to investigate the transformer that steps down the voltage before it enters the machine. Begin by inspecting the transformer for any visible damage or signs of overheating. Look for cracks, leaks, or corrosion on the transformer enclosure. Check the bushings and terminals for any signs of arcing or flashover. If the transformer appears to be physically damaged, it should be replaced immediately. Next, use a voltmeter to measure the voltage at the transformer input and output terminals. Compare the measured voltages to the transformer's rated voltage levels. If the output voltage is significantly lower than the input voltage, it could indicate a transformer problem. A low output voltage can be caused by a variety of factors, including insulation breakdown, winding faults, or core saturation. To further investigate the transformer's condition, it may be necessary to perform additional tests, such as insulation resistance testing or turns ratio testing. An insulation resistance test measures the resistance between the transformer windings and the transformer core. A low insulation resistance reading indicates that the insulation is degraded and needs to be replaced. A turns ratio test measures the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. An incorrect turns ratio indicates that there is a fault in the transformer windings. If the transformer's output voltage is within the rated range, the next step is to check the transformer load. Determine if the load on the transformer is within its rated capacity. Overloading a transformer can cause it to overheat and produce an undervoltage. Use an amp meter to measure the current drawn by the CNC machine. Compare the measured current to the transformer's rated current capacity. If the current exceeds the transformer's rated capacity, reduce the load on the transformer or replace it with a larger transformer. Finally, consider the age of the transformer. If the transformer is older, it may be more likely to fail. Older transformers are more susceptible to insulation breakdown, winding faults, and core saturation. If the transformer is more than 20 years old, it may be prudent to replace it with a new transformer. If you are unsure about the transformer's condition or how to troubleshoot further, consult with a qualified electrician. A qualified electrician can perform a thorough inspection of the transformer and identify any potential problems. They can also perform any necessary repairs or replacements. In summary, transformer failures are not common, but they can occur. When troubleshooting an undervoltage alarm, it is important to thoroughly investigate all potential causes, including the transformer. By following these steps, you can identify and resolve the issue, restoring the CNC machine to proper operation. In addition to the troubleshooting steps mentioned earlier, there are some other factors to consider when dealing with transformer failures. Firstly, it is important to ensure that the transformer is properly grounded. A good ground connection helps to protect the transformer from voltage surges and reduces the risk of electrical shock. Secondly, it is important to protect the transformer from environmental hazards such as moisture, heat, and chemical contamination. Use a weatherproof enclosure to protect the transformer from moisture. Provide adequate ventilation to prevent the transformer from overheating. Avoid exposing the transformer to corrosive chemicals. Thirdly, it is important to perform regular maintenance on the transformer. This includes inspecting the transformer for any visible damage, testing the insulation resistance, and cleaning the bushings and terminals. Regular maintenance can help to identify potential problems before they escalate into major issues. Fourthly, it is important to keep accurate records of transformer maintenance and repairs. These records can be helpful in troubleshooting future problems and determining when the transformer needs to be replaced. By following these guidelines, you can minimize the risk of transformer failures and ensure reliable power supply for CNC machines and other industrial equipment. Furthermore, understanding transformer nameplate data is crucial for proper selection, operation, and maintenance. The nameplate provides essential information about the transformer's characteristics and capabilities. Key parameters include the kVA rating, which indicates the apparent power the transformer can deliver without exceeding its temperature limits. Voltage ratings specify the primary and secondary voltages for which the transformer is designed. The impedance value, expressed as a percentage, is vital for calculating short-circuit current and coordinating protective devices. Frequency rating indicates the frequency of the alternating current for which the transformer is designed, typically 60 Hz in North America. Insulation class specifies the maximum operating temperature of the transformer's insulation system. Vector group describes the phase relationship between the primary and secondary windings, which is important for paralleling transformers. Understanding these nameplate details ensures safe and efficient transformer operation. When addressing undervoltage issues, it's also wise to investigate the incoming power quality. Power quality problems like voltage sags, swells, and harmonics can negatively impact transformer performance and contribute to undervoltage conditions. Voltage sags are short-term reductions in voltage, while voltage swells are short-term increases. Harmonics are distortions in the sinusoidal waveform of the alternating current. These issues can be caused by various factors, including utility grid disturbances, heavy equipment startup, and nonlinear loads. Monitoring the incoming power quality with a power quality analyzer can help identify and mitigate these problems. Installing surge protective devices can protect the transformer from voltage spikes and surges. Implementing harmonic filters can reduce harmonic distortion and improve power quality. Additionally, ensuring proper wiring and grounding practices can minimize voltage drops and improve overall system performance. The National Electrical Code, or NEC, provides guidelines for the safe installation and operation of transformers. Article 450 of the NEC covers transformers in detail, addressing topics such as overcurrent protection, grounding, ventilation, and location requirements. NEC Table 450.3 provides guidance on overcurrent protection for transformers rated over 600 volts. NEC Section 450.13 covers transformer accessibility, requiring adequate working space around transformers for maintenance and inspection. Adhering to the NEC ensures that transformers are installed and operated safely, minimizing the risk of fire, electrical shock, and equipment damage. Proper transformer maintenance also includes regular testing of the transformer oil in oil-filled transformers. Transformer oil serves as both a coolant and an insulator, and its condition can indicate the health of the transformer. Oil testing can identify contaminants, moisture, and other issues that can degrade the oil's performance. Dissolved gas analysis, or DGA, is a common oil testing method that detects the presence of dissolved gases in the oil, which can indicate insulation breakdown or other internal problems. Based on the DGA results, corrective actions can be taken to address any issues and prevent transformer failure. Oil filtration can remove contaminants and moisture from the oil, extending its lifespan and improving its performance. Regularly testing and maintaining transformer oil ensures reliable transformer operation and prolongs its service life. Furthermore, consider the impact of ambient temperature on transformer loading. Transformers are designed to operate within a specific temperature range, and exceeding this range can lead to overheating and reduced lifespan. High ambient temperatures can reduce the transformer's ability to dissipate heat, leading to higher operating temperatures. Directing the transformer's load capacity based on the ambient temperature can prevent overheating and ensure reliable operation. Directing factors are typically provided by the transformer manufacturer and should be consulted when operating transformers in high ambient temperature environments. Maintaining proper ventilation and cooling can also help to reduce the impact of ambient temperature on transformer loading. In addition to the above considerations, it is important to document all transformer inspections, testing, and maintenance activities. Maintaining detailed records allows for tracking transformer performance over time and identifying potential problems early on. The records should include information such as the date of the inspection or test, the results of the inspection or test, any corrective actions taken, and the name of the person who performed the work. These records can be invaluable for troubleshooting future problems and making informed decisions about transformer maintenance and replacement. Finally, consider the potential for transformer upgrades or replacements. If the transformer is consistently overloaded or experiencing frequent failures, it may be necessary to upgrade to a larger transformer or replace it with a more reliable model. When selecting a replacement transformer, it is important to consider the load requirements of the CNC machine, the incoming voltage and frequency, and the environmental conditions. Choosing the right transformer ensures reliable power supply and minimizes the risk of future problems. Furthermore, energy-efficient transformers can reduce energy consumption and lower operating costs. These transformers utilize improved core materials and designs to minimize losses and improve efficiency. While energy-efficient transformers may have a higher initial cost, they can provide significant cost savings over their lifespan. By considering all of these factors, you can ensure that the transformer is properly selected, installed, and maintained for reliable and efficient operation.